This is part 4 in a series of videos in which I'm working on a PDP-8M vintage computer. I'm repairing and restoring it, and in the first 3 videos I stripped the chassis down, corrected a fault with the power supply. In this video I was going to just jump straight in and fully test the supply. Now it's been rebuilt, but something came up in conversation since the last video that I thought I'd mention here. And that is the use of riser cards in the PDP-8 machines. If you're not familiar with riser cards, this is an example of a riser card. This is actually off an HP machine, but same sort of idea. The idea is you plug the board in you want to test, and it allows you to raise the board out of the machine, and then you can access it. Otherwise these are all in the rack and you can't really easily access them. I do have some riser cards for the PDP machines. Well, one of the main complications on working on these computers is, if you look at the top, a lot of the cards have these cross-link connections. So there's a small jumper board joins 2 or more cards together. So for example, the register cards are in a pair, the memory cards are at least 3 cards, and so if you want to raise one of them, you have to raise all the ones that are interlinked, and you very quickly run out of riser cards. In fact, the riser cards I have for the PDP machines are currently plugged into another machine I'm working on. Otherwise I'd show you what they look like, but essentially it's half width card that has no components on, and it just connects the bottom connections to edge connectors at the top. The ones I have I purchased some time ago, and it does use standard PDP connectors, as you see on the motherboard and cross-link connectors. The problem is they're quite hard to get hold of, quite expensive, and so I started making my own riser boards, and that's what I want to just mention here. Is I'm about to order some more, so if anyone wants any, then let me know, and I'll wait another few days before I place the order. If you want any riser cards, let me know and I'll add some more to the order. I'll make them available on my website. The way that the riser cards work is they are full-sized cards. They have the full height and spaced connectors at the bottom, and then they have the equivalent of these connectors at the top. But as I say, the issue is trying to find suitable connectors to populate the riser card. And one of the connectors I supply is for the Altair 8800 vintage computer, and that uses boards that have exactly the same pitch as the PDP boards. So this is an Altair board, and if I offer this up, you can see that the spacing of the connections along the edge connector is exactly the same. So I use these connectors to populate the PDP riser cards, and the way I do this is so I don't have one to show, they're all currently in use, but the card looks like this. It's just taller and wider, and it has edge connectors at the bottom, and then the connector is fitted like this at the top. But as you can see, there are these big cutouts in the connector along the bottom. So the way I do this is I take one of the connectors for the Altair, I remove the pins, and I cut them down. So 2 of these will make up a complete connector. But what you don't want, of course, is to have these offset. One of the strange things about the connectors on the PDP is there is no shoulder on the end of the edge connector. So if we look at this, you'll see that the last contact is right up against the end of the connector, whereas if we look at a standard card, you'll notice there is quite a lot of board extending past the last connection. And then if you look at the connector, you'll see that there is provision for that, and that allows the board to be properly located. The problem when you use these, of course, with the PDP is it allows the boards to be put in offset. So I don't know if you can see this very clearly, but we're very close to shorting out 2 of the, or every pair of the connectors along the bottom. So we need some way to locate this on the edge connector. So what I do once I've removed the pins is I 3D print small infills. These press into the connector, so quite a tight fit, but they press in. I won't push it all the way in now. And there's one of these for each of the two halves. So it's basically 4 pins moved off each, or removed off each side, so they will push all the way in. I push it all the way down, and then in the centre there's a double one. The centre slot is half the width of the outside slot, so then there's a centre one that goes in, and that, again, I won't push it all the way down, and again that holds the two together, and this is then soldered to the top edge of the riser board. And then when you come to plug them together, this gives you exact registration of the board with the connectors, so hopefully you can see all the connectors are perfectly aligned and the board cannot move side to side. There's about 1/4 millimeter play with the infills that I've made. So that's the way I do this. Now if you want any riser boards, then let me know and I'll order some extra. I'm not quite sure exactly what the price will be yet. I'm suspecting they'll be around £25 each, but I will let you know that as soon as I've got a quote back from the board manufacturer, and I will make those available on my website, and then you can either source your own connectors or you can buy the Altair connectors off my website. So that's the solution I'm using for risers, if anyone is interested. So now we'll get on with the purpose of this video, which is to test the repaired supply. Okay, so testing the power supply. I've already done static tests, so I've tested the capacitors and checked for any shorts, and we've already powered this up in the previous video and the voltages seemed fine. But now we need to run it up to full power and to adjust the rail voltages. It is quite critical on this machine. The voltages are correct. The core memory is very sensitive to power supply issues, and so the accuracy to which you adjust the supply is quite important. So the first thing I do, you notice this is not currently connected to the bench supply, so this is not plugged into the mains at the moment. The first thing I want to do is check the crowbar protection for the individual rails. So if we look at the schematic again, then we'll see that the crowbar protection is formed with this device and this divider network. So the way this works is that as the voltage on the rail, this is a 5-volt rail, starts to rise, it pulls up the gate voltage of this device, this is a thyristor, and once the gate voltage exceeds a certain level, then this will turn fully on, and effectively it is then a short circuit, and this is connected through a very low value resistor to the incoming DC rail. Quite often this is shorted through the main supply only, so the current limit kicks in rather than doing what this supply does, which is to just short circuit the input. Because we're short circuiting the input here, we've got to be fairly careful, because if we try and do this with it plugged into the mains, if we do trigger the over voltage protection, it will just blow the fuse. So what I've done is I've disconnected one end of the fuse, and we're connected to this point with the bench power supply. I'm going to power it up. We'll check the output voltage. We can see if we can adjust it. Chances are we won't be able to adjust it high enough to trigger the crowbar protection, so we might have to try a different method for doing this, but we'll try that first. But as I said, if you don't disconnect the fuse, although in theory you shouldn't get anything going back through here, what will happen when the thyristor turns on, because we've got such huge capacitors here, we've got 24,000 microfarad capacitor here, so what will happen is it will blow the fuse, because effectively the capacitor is charged up through the fuse, and then when we short circuit this side, it will connect the capacitor through the fuse to ground, and it will most likely blow the fuse. So I've got the fuse disconnected, and what we'll do now is we'll power this up. I've got the bench supply current limit set to 200 milliamps, which is easily enough to power this circuit, and we should see an output on the 5-volt rail. The meter is connected to the output of the 5-volt rail. So we'll power up the bench supply, and as we can see we are getting 5 volts. We'll try to adjust that. I'll try initially to adjust it too high and see if the crowbar protection kicks in. And it is very important on these machines that it works, otherwise you can end up with a faulty supply destroying every board in the machine. So that's now turned all the way up, but it's not quite high enough. The other voltage on these is normally between 6.6 and 6.7 volts, so we're just slightly under that. So I'll go back down to the correct voltage, and we'll adjust these again once we've got a load on them, and I'll check it again once it's in the machine. I tend to start with them fairly low, and then if we need to we can raise them slightly. What we can do now is actually connect an external supply to the 5-volt rail, and what will happen is this will effectively shut this down, because the feedback loop will tell the control loop that we've got plenty of voltage here and there's no need to pass any more current. So it will effectively shut this down, we won't do any harm, and once we exceed the crowbar trigger threshold, then we should see the voltage suddenly drop to very close to 0. So we'll try that now. I'll just connect another channel on the bench supply, set that to 6 volts. I'll turn that on. So what I'm doing now is turning on the second supply, which is connected to the 5-volt output rail, and it should then switch over from this supply supplying the power to the bench supply supplying the voltage, and we should see it rise. So I'm turning it on now. As we can see, it's gone up to 6 volts, which is what the bench supply is set to. I'll get up to 6.6 volts, 6.7, 6.8, and we should see it shut down fairly soon. Okay, and there it goes. It's now shut down. The power supply is still powered up, but the crowbar has kicked in, and as you can see it's clamping the voltage down to near 0, and it will stay down until I cycle the power. So I'll now cycle the power back on, and you can see the 5-volt rail has indeed recovered. So I'm just going to trim that back down to 5 volts, and that will be our starting point. And I'll do the same thing with the plus 15 and the minus 15 volt rails, and then we'll get the mains connected and the electronic loads in circuit and start doing a full power test. Okay, I've got everything hooked up. I've got the supply hooked up to the bench auto transformer. I've got the 3 output rails from the supply connected to 3 Kunkin KP184 electronic loads. The one on the right is connected to the plus 5 volt rail, the one in the middle is connected to the plus 15 volt rail, and the one on the left is connected to the minus 15 volt rail. Now the one on the left is connected in reverse. It won't work with negative voltages, so it will show positive voltage, but just bear in mind that it is a negative rail we're looking at, so the positive input is connected to ground. I've got them set up initially for constant resistance, so we have the 2 on the left set to 200 ohms and the one on the right on the 5 volt rail is set to 100 ohms, so we'll start off with a fairly low current, and I'll power it up and see if we get any voltage indications on the loads. So a big surge as the big capacitors charge up in the supply, but we can see that we have indeed got some sensible voltages showing on these supplies. So we'll start to ramp up the current. We'll start by switching them all on, and we're getting very low currents, about 50 milliamps for the 5 volt rail, about 75 milliamps for the 2 15 volt rails, which is correct for the resistance we have set. Now the specification for this supply, it says that the 5 volt rail should be able to give out up to 17 amps. The plus 15 volt rail should be able to give out 1 amp, and the minus 15 volt rail should be able to give out 5 amps. But we'll go up to 12 amps for the 5 volt rail and the full 1 amp for the plus 15 and the full 5 amps for the minus 15, and we'll see if it survives. And if it does, I'll leave it running for several hours, make sure it's okay. I will need to put the top cover on, or a top cover on this, when I'm doing the soak test, otherwise it won't blow enough air across the heatsink. If you recall, I did refit the foam on the underside, so we get good airflow down here. But I'll start off, at the moment it's fairly cool, it'll start heating up quite quickly, so we'll start with the cover off because I want to be able to access the pots if I need to make any adjustments. So we'll increase the current on the 5 volt rail, and we're now getting around 100 milliamps, and the voltage is still looking fine. And we'll keep going up. So at 250 milliamps, still looking fine. I've got the auto transformer set to 120 volts, by the way, in case you can't see it. So at half an amp. ,630 milliamps. And we're now at 1 amp. Voltage has dipped a little bit, we'd expect that from fully unloaded, but now the curve should start leveling out and we should see much less variation as the load increases. So we're now at 2.5 amps. .8 amps. .1. Now at 4.5 amps, still looking fine. We're at 4.5 volts, so it has dropped quite a bit. Now some of this will be in the leads that I'm using. I could use the remote sense, but as I say, I'm going to set this on the low side and readjust it once it's in the machine. I'm just here trying to prove that the supply is working the way it's supposed to. Okay, I can't really go any higher than this without putting the cover on the top, otherwise it will overheat, and I will quickly switch the current up for the other 2 rails. So we want really 1 amp on the 15 volt rail. And that's looking fine, and the same thing with the minus 15 volt rail. Okay, well clearly we had a failure of some sort there, and I checked, and what had happened is the crowbar protection had cut in for the 5 volt rail. I've cycled the power and it came back up again, but then it did the same thing when I ran it back up to a fairly high load. say a fairly high load. It was only about between 6 and 8 amps, and this 5-volt rail is supposed to be rated up to 17 amps peak. The overcurrent protection is about 24 amps, and the over voltage is supposed to be between 6.8 and 7 volts, and we were sitting around 5 volts. Something fairly odd is going on. Now, it might seem odd that we can have all this power because the raw DC rails are over 30 volts, so feeding that through into 5 volts means, in theory, we get a huge amount of dissipation if this was a linear supply, but it's actually not a linear supply, it's a switching supply. The various rails are essentially kind of Schmidt triggers that are cycled fully on or fully off depending on whether the required rail voltage is above or below a specified value, and that value is what you set with the pots. So the power devices, the pass devices, are either fully on or fully off, and it makes it very efficient and you don't get huge amounts of dissipation. Having said that, this was getting really hot, and although the thermal cutout didn't kick in, it was getting much hotter than I would have expected. And we were only up at about a third to a half of the full power output for the 5-volt rail. So something strange is going on. But as I say, it did come back up again when I recycled the power, but I suspect there's something wrong with the main pass transistor for the 5-volt rail. So this is a 2N5302, so it should handle 30 amps. But bear in mind this is pulsed, so it does need to be able to handle that full current. Now it could be there's something wrong with some of the other components around it, so I'll need to check that. But the first thing I'm going to do is, as we have it standing by for other experiments, we'll try putting this into the curve tracer and see if there's anything wrong with this. It could be this is leaky and it's not switching quickly enough. So we'll put this into the curve tracer and see what it does. Okay, so I've got the curve tracer on the bench, and to start with we'll test a known good device. So I've got 2N3055 inserted into the adapter. Similar sort of transistor, not as high current, but as I say, I'm testing for leakage of basic operations. So we'll plug that into the fixture and just set it up now. We want to have a step generator, and we'll start off at 1 milliamp and work up from there. Maximum 25 volts. Okay, so we should be able to get a curve, get a slightly lower resistor, and I'll turn the lights off so you can see the screen on the curve tracer more clearly. And as you can see, that's behaving exactly as we'd expect a bipolar transistor to behave. I'll increase the current, so we're currently at 1 milliamp per vertical division, so we'll go up to much higher current. We'll go up to 100. And of course we'll need to reduce the resistor, but as you can see, still working fine. And so we're up about an amp maximum collector current here on the screen, and it's working fine. We could keep going. This will supply up to about 20 amps, but there's no need to do that here. I'm just trying to get some idea as to the general operation of the transistor. If we see anything weird, we can go into it in a bit more detail. So we'll go back down to 1 milliamp. And what I can do now is swap this device for the one that came out of the power supply. So I'll just pop that out, and we'll put our suspect device into the adapter, plug that back in, and we'll rerun the test. Now this should give us identical set of curves or something very close to it. Okay, so we're getting okay. This transistor has very high leakage. It is switching, which is surprising in the supply. I'm suspecting it's actually because it's got such a high drive, and possibly the driver transistor in the power supply is responsible for doing the switching. This is not actually doing much. So I'll need to replace this. It did test good. It still does read reasonably well with a multimeter. If we put it into diode test mode, it does still test as you'd expect an NPN transistor to test. It's just obviously not working the way it's supposed to. It's acting more like just a piece of wire. So what I'll need to do is get a replacement transistor ordered, and we'll get that fitted to the supply. But I think we need to investigate the power supply for the PDP in a much more in-depth way. There's obviously something not right with it, whether it is just this transistor that's at fault or if we've got an issue with some of the other switching components. It does regulate, it regulates within the limit, but as I say, the crowbar kicks in at between 6 and 8 amps, so there's something not right, so we'll need to throw the scope on it. But I'll do that in the next video. I'll get a replacement transistor, we'll get it fitted, and then we'll go from there. But clearly we can see there's something wrong with this one. So this does of course highlight the importance of testing power supplies very thoroughly when you're working on old equipment. Had we just thrown the power supply back into the chassis when it tested nominally good, we could have ended up destroying the boards in the machine if they're not already damaged. But either way, we need to get the power supply working in a stable way before we proceed. There's no point messing about with a dicky power supply and risking damaging very rare boards. Now I may well run the backplane from the bench supply anyway for the initial testing, so we don't need the supply, but I don't want to use this supply until I'm fairly confident that it's working properly, and at the moment I think there are some major issues with it.